So we've reached the second stage of the project, and this will wrap up on the 6th of March when the deliverables will be due, and we will begin the towards and final stage on the 13th of March. So what we're doing now is we're going to incorporate the propulsion system into the boat, which is the small water pump. And what you do is you design a pipe network to draw that fluid in and expel it out, and it will go out at a higher volumetric flow rate and pressure. And that will provide the propulsion force to move the boat forward. You see different designs from other groups in the past. And what you can do is you can extract the dimensioned drawing from the outlet pipe, and we will apply the theory to that. So we'll adopt these two Excel sheets to produce a pump characteristic curve and a pipe characteristic curve that will identify an operating point, and the operating point will tell us the flow rate that we will get from the pump when it's attached to this outlet pipe. In other words, the flow rate here. And it also tells us the head loss, how much pressure losses we incur as the fluid tries to go through that outlet pipe. The lessons we're trying to convey at this point of the course are the principles, the fluid mechanic principles of centrifugal pump theory and hydraulic networks. So to get those messages and those lessons across, what we'd like you to do is simplify your outlet design, your initial outlet design. And when you do that, what we should find is we should find the operating point moving to the right to give us an increased flow and less pressure loss. We will also then add a nozzle in on the end. And what the nozzle will do is it will increase the velocity of the fluid at the expense maybe of a bit of pressure loss, and increase the velocity of the fluid coming out of the pipe network and give us that little bit more propulsion. So this is the propulsion systems, the pump, the battery to drive it, the tubing and elbows to be arranged in different configurations like these to produce the pipe network. And then you can design the nozzle yourself to add into the end of the pipe to give it that more propulsion. I've updated the spec sheets. They're up on Loop for the information, hopefully is a bit more clear. So the deliverables for this stage of the project is, first of all, a poster. On the poster, give us a CAD view of your boat that incorporates the pipe network. Give us an extracted dimensioned drawing of the pipe, and then your HQ diagram identifying the operating point for the first version of your outlet pipe and for the second version of your outlet pipe. You can add in details on the nozzle too, if you want. The presentation will be elaborating on all that, explain why you designed your pipe network that way as opposed to maybe any other way. You'll have to interact with this spreadsheet also to explain how you calculated the pressure losses from your pipe system. And to do that, you'll be describing how you calculated Reynolds number, friction factor, major head loss, minor head loss, and operating point for your pipe system, which are all fundamental principles of fluid mechanics. The theory is up on Loop. Simply describe the stage 2 theory, and it focuses on hydraulic networks. So I'll just briefly go through the theory related to this stage of the project, and I'll begin with very first principles. So pressure equals force over area, and if we have a force acting down over cross-section area like this piston cylinder arrangement here, the pressure is that force divided by that area in newtons per meter squared or pascals. And that pressure is transmitted to every fluid particle, whether it's a liquid or a gas, uniformly, and it acts perpendicular to the sides, regardless of whether they're curved or straight. 100 kilonewtons per meter squared equals 100 kilopascals equals 1 bar, which is another common way of expressing pressure. So that's the general term for pressure, and it applies to solids, liquids, and gases. But in fluid mechanics, we're specifically interested in hydrostatic pressure. And that's the pressure that's exerted by a fluid at a given point within the fluid due to the forces of gravity. Elaborating on that hydrostatic pressure increases in proportion to the depth measured from the surface because of the increasing weight of fluid exerting downward force from above. So if you dive into the sea, you'll have a pressure force, hydrostatic pressure force around you. Deeper you go, the greater that will get. It come to some point where you will need maybe a protective suit or even a protective vessel to protect you from those increasing hydrostatic pressures. It's the reason why dams are thicker at the base than they are at the top, to withstand the increasing hydrostatic pressure forces acting deeper below the surface of the water. So we calculate hydrostatic pressure by multiplying the density of the fluid by the acceleration due to gravity by h, which is the distance from the point we're measuring up to the free surface. So it's very different than the normal way we calculate pressure, but the units are the same: newtons per meter squared or pascals. So the Pascal is named after French scientist Blaise Pascal. He once came up with Pascal's paradox, which simply states that if you have vessels or containers of different configurations, in other words, different volumes, filled up the same level with the same fluid, the pressure at the base will be the same. That's because they're independent. It's independent, the pressure is, of volume. So if you look at the equation again, density, acceleration due to gravity, h, so volume is not taken into consideration. So that's the paradox. So in this particular case, what we can do, because we're dealing with water, we can drop the density because the fluid is consistent. The acceleration due to gravity is a constant, so we can drop that. So we can simply express the pressure in terms of that elevation h, and we call it meters of water pressure or pressure head. Now that's important because when it comes to specifying a centrifugal pump, the pressure is often specified in meters of water pressure. So for example, here we have a centrifugal pump, and the way they work is that when you switch it on, the fluid is drawn in to the eye of the impeller. The impeller rotates and sends the fluid out at higher volumetric flow rate and pressure due to centrifugal force of the rotation of the impeller. So if you were to take the outlet pipe of your centrifugal pump that you're given for this project, it's specified as being able to deliver 3 meters of water pressure. So if you point that tube up in the air, the fluid will go up 3 meters in the tube before stalling at that point, because there's not enough pressure being delivered by the pump to push it any higher. If, on the other hand, it was specified as being able to deliver 8 meters of water pressure, it will go up 8 meters in the air before stalling at that point. And that's a way to think about the type of pressure that's being delivered by your pump. And that's important because when it comes to characterizing a centrifugal pump, describing the characteristics, the relationship between pressure and flow rate, the pressure is often expressed in meters of water pressure, and the flow rate in terms of your pump will be meters cubed per second. So this is referred to as a HQ diagram. And on it, we plot the pump characteristic curve here and the pipe characteristic curve here, where the intersect is the operating point that determines the flow rate we'll get from that pump when it's attached to that pipe network, and also tells us that the pressure losses that we'll induce as well. So how is these characteristic curves formed? Well, let's start with the pump characteristic curve. If you switch on your centrifugal pump, it'll draw fluid in through the eye and expel it out the outlet tube. While it's running, if you momentarily switch it off, the outlet valve off, keep the pump running, switch the outlet valve off, the pressure will build up across the pump. And in your case, it's 3 meters of water pressure. You can do this momentarily with a centrifugal pump because it's regarded as a non-positive displacement pump. There's clearance between the impeller and the housing. So you got maximum pressure at zero flow rate. And as you open that outlet valve, the flow rate starts to increase and the pressure starts to drop across the pump. If you get enough data points, you collect this curve that we call the pump characteristic curve, identifying the relationship between pressure in meters of pressure head against flow rate in meters cubed per second. So your pump is already being characterized for you. In the pump curve measurements Excel sheet, you've got the meters of pressure against meters cubed per second flow rate. You've also got those in other units, such as bar and liters per minute. And this is the plot here. So that's already been done. What you need to do is you need to design your outlet pipe here and produce a pipe characteristic curve to get that operating point. That flow rate value will feed into the third and final stage to help us calculate the velocity of the boat. So how do we calculate this pipe characteristic curve? As the pump starts to push the fluid through this outlet pipe, there is losses incurred due to friction between the fluid and the inner wall of the pipe in the straight sections. We call them major losses. And minor losses as the fluid tries to navigate around bends and fittings and valves, like these 90-degree bends and the converging nozzle at the end. So what we do is we add up all the major and minor losses for a particular flow rate. We get a point on the curve, and then we do that over a range of flow rates to get a full pipe characteristic curve. So how are these losses calculated? To explain that, we need to begin with Bernoulli's equation. Bernoulli's equation was first published by Daniel Bernoulli, who was a Swiss mathematician in 1738. And what it does is it applies the conservation of energy to pipe systems. So we can see that pipe systems can be very complicated in pharmaceutical, chemical companies, and so on. So what we'll do is we'll take a very simplified approach to it. Applying the Bernoulli's equation, we say at this point where this pressure gauge is, the energy at this point due to the pressure that's pushing the fluid through the pipe, due to the velocity, how fast it's going, and due to any elevation difference, is equal to the pressure or the energy at this point due to the pressure, the velocity, and the height difference. So over here we see the velocity term. We see the elevation term, and we see the static term. They are expressed in such a way so that their units are ultimately in meters. So this is the dynamic or the velocity head in meters due to the velocity, basically the kinetic energy. This is the elevation head in meters due to any height difference. So you're looking at potential energy there. And then you've got the pressure and energy component as well. So we sum them up at one point in the pipe system, and they should equal them summed up at another point in the pipe system. However, what the Bernoulli's simplified version of the Bernoulli's equation doesn't tell us are those losses that we're looking for, because of all the energy at this point will not be transferred to this point due to losses. Losses due to friction between the fluid and the inner wall of the pipe in the straight sections, and minor losses as the fluid tries to navigate around bends, fittings, and valves, and so on, like this converging nozzle. So those head losses there are effectively the difference between each term in the Bernoulli's equation. And there's two ways of obtaining those values. We can either get a pressure reading at one end of the pipe and a pressure reading at the other end of the pipe. The difference between the two is those losses in terms of pressure. And another way of doing it is by using equations. So this is the major loss equation, and this is the minor loss equation. In this particular pipe network example, we have 3 straight sections, 3 of them of different lengths, and one that has a different diameter than the other 2. And there will be major losses in them. And then we will have minor losses at the converging nozzle the 180-degree bend, the inlet and outlet here, which are fittings of sorts. So what we do is we apply these two equations and calculate the major and minor losses for a particular flow rate. And then we do that over a range of flow rates to get the whole curve. So let me explain how those two equations work. For the straight sections, you've got the length of the pipe, you've got the velocity of the fluid going through the pipe, you've got the diameter, inside diameter of the pipe, and you have 2 times the acceleration due to gravity, and you have this friction factor value F. So the friction factor can be obtained by the Moody diagram. So how the Moody diagram works is if you know the surface roughness on the inside of the pipe and you divide it by the inner diameter of the pipe, you'll get your relative roughness. And that identifies a position along this y-axis and identifies one of these curves. Let's say this one, for example. Then we calculate Reynolds number. Over here, you'll see 2 ways in which we can calculate Reynolds number. And Reynolds number describes the nature of the fluid flowing through the pipeline, whether it's turbulent or laminar, for example. So we get a Reynolds number value, we go straight up, intersect the relative roughness curve, and then go over to the left to the friction factor value over here on the other y-axis. So that's how we calculate the major losses in the straight sections. For the minor losses, we've got the velocity of the fluid, we've got 2 times the acceleration due to gravity, and we have this K factor or loss coefficient. The K factor or loss coefficient is obtained experimentally by suppliers of valves and fittings and so on. So what they would do is they'd run through many tests, find out what that loss is, and then outline it in tables and charts and so on. So for the 90-degree elbow, the K value we can take is 0.75. If we don't know the velocity, we can get it from the volumetric flow rate, because the volumetric flow rate equals the area multiplied by the velocity. So there's a lot of calculations to be done and over a range of flow rates to produce that pipe characteristic curve. Thankfully, we have this spreadsheet here that will help us to do that. And what I'm going to do is I'm going to open that spreadsheet up and I'm going to explain how it's used. Okay, thanks.